In this lecture, we're going to start with the analysis of entropy change. From the analysis of entropy change, we are going to generate two important conclusions. Entropy generation, entropy balance equation. Both are for closed systems. And these two important concepts of this chapter will then be applied to the analysis of heat engines and heat pumps. Here, let's look at a cyclic process involves two segments. The outgoing segment from state 1 to state 2 is irreversible. The returning trip is reversible. If we would like to integrate dq over t for this complete cycle, this integral can be broken into two parts. And based on the discussion of Clausius inequality, we know the second term, the combination of these two terms is smaller than or equals 0. Let's look at the second term alone. From state 2 to state 1 through a reversible process. Because it's reversible, then the dq divided by t essentially is the definition of entropy change. This ratio for a reversible process is independent of path. This is how entropy was defined. Therefore, we can express this integral as the difference between the entropy at the state 2 to state 1. Substituting this integral in equation 1, we get this expression. And rearrange this expression, we get this equation. The physical meaning of this equation is that entropy change from state 1 to state 2 for an irreversible process is greater than or equals this integral dq over t. And for the reversible case, the equal sign prevails, and the greater sign applies to the irreversible process. If we look at the small change, we see that ds is going to be greater than dq over t, greater or equals than dq over t. Equal sign applies only for reversible process. Greater sign applies to all irreversible process. This expression can also be expressed in specific entropy change format. And if we like to remove this inequality sign by equal sign, we see the difference between the two terms has to be a term greater or equal to 0. So this is the term we called entropy generation. And this term always greater than or equals 0. And when we leave this slide, we also have to know one more important thing. Because dq can be either positive or negative, ds can still be positive or negative. Entropy generation indeed will be positive. dq for a control volume which absorbs heat. The first term on the right is a positive, and the combination of two positive terms is a positive quantity. If the control volume rejects some heat, dq is negative. So dq over T is negative. The combination of these two terms can be a positive or negative. So if we draw what we just discussed on the TS diagram, if we start from a state as this dot on the TS diagram, the change can be any direction on the TS diagram. If Q is a positive, we can say for sure it moved to the right. If heat is rejected from the control volume, Q is negative. So the arrow point to the left. But the combination of these two terms can be either positive or negative. Then let's look at the energy generation equation in different aspects. It will generate the concept of lost work. This is the equation we just saw. And rearrange and solve for dq, we get this expression. And from chapter 3, the total energy change of a process equal to dq minus dw. That's first law. By definition, total energy is a combination of internal energy, kinetic energy, and potential energy. So then from Gibbs relation, we have the third equation on this slide. Now we can replace TdS in this expression by this expression and place dq into this equation. Then we get this portion of the equation. Rearrange, solve for dw, we get this equation. And if we compare this equation with the equation we saw for reversible process we discussed in chapter 3, we see the only term which is different from this equation is this term, TdS generation. So the physical meaning for this comparison is this is for irreversible process. And it differs from the reversible process by this factor. So if we interpret dW as the available work, we lost some work due to the irreversibility. Therefore, this term is called lost work. And notice the lost work is directly proportional to an entropy generation. Then if we look at the equation in dynamic format, that means if we divide the equation we just saw by dt, we get this equation in differential form. This becomes the rate of heat transfer. The third term becomes rate of entropy generation. And if we integrate this dynamical equation from time 1 to time 2, we get the entropy change of a control volume between two different times equal to the integral of dq over t of the control surface from time 1 to time 2 plus the entropy generation between time 1 and the time 2. In both expressions, the entropy generation term have to be positive or equals 0. This slide compares the energy balance equation to entropy balance equation. First law has three terms. Rate of total energy change equal to Q minus W. For the entropy balance equation, we have a generation term, the flux due to heat transfer. On the right, we see the control volume denoted by this black curve, and its surface has a temperature denoted by T sub Cs. Control volume, control surface, temperature of the control surface, and if we have a heat transfer, it causes irreversible heat transfer. It causes an entropy generation. And entropy generation can also be caused by different other processes like friction, plus deformation, end strength, gas expansion in the cylinder, current through a resistor, and the combustion process, etc. In the next few slides, we're going to see examples that the heat transfer due to the temperature difference between the control volume and the surrounding, it causes irreversibility. And the irreversibility is a major source of the rate of entropy generation. Here is the first example. If we have a thermal pan window with two pieces of glass, and between the two glass, we have gas filled between the two glasses. Assuming it is a summertime, temperature outside the house is higher than temperature inside the house. So heat will be transferred from outside to the gas, and then the gas will provide heat to the room. If we take a control volume, like we draw in red, there are two heat transfer terms associated with this control volume. One is heat transfer from outside to the control volume. The other term is heat transfer from the control volume to the inside of the house. So there are two heat transfer terms. Let's represent these two heat transfer terms as two positive quantities. They have to be identical in absolute value because the process is in the steady state. So we have Q1 minus Q2 equals 0 in the steady state. They have the same absolute quantity if we assume both quantities are positive. This is the heat transfer leaving the system. That's why it has a negative sign before it. if we look at the entropy balance equation, it will involve two heat transfer term and the heat entropy generation term. In the steady state, the left-hand side is 0. So we can rearrange this equation to estimate the entropy generation rate equal to the heat transfer rate divided by this T2 room temperature divided by minus Q1 dot divided by T1. Rearrange because Q2 dot equals Q1 dot. We can take the common factor out. We get this factor on the right. Because during the summer, T2 is lower than T1. Therefore, the first term is greater than the second term in the parentheses. So this entire term is a positive. So we can conclude in the summer, this heat transfer process generate entropy like this. In the winter, we have T1 lower than T2, and the heat transfer going in the opposite direction as the summer. Through the similar analysis, we should be able to generate the same conclusion. The entropy generation rate is positive. Please generate those terms in between. See if you can generate the same conclusion. This is a good exercise. If we look at the second example, which is related to water vapor condensation. If 1 kilogram of saturated water vapor at 100 degrees C is condensed to saturated liquid at the same temperature, 100 degrees C, then we are asked to analyze the net increase in entropy of the condensation process plus the entropy change of its surrounding, if the surrounding is at 25 degrees C. Let's look at the water vapor. The entropy change can be directly read from the steam table, saturated steam table, because the mass of the steam is given. Specific entropy change of evaporation is tabulated. So we can estimate entropy change. It's a negative quantity. If we look at the entropy change for the environment, we have to estimate heat transfer first. Heat transfer to the environment is essentially Q based on the first law. During the water vapor condensation, the heat give away from the vapor goes to the environment is in same amount. So in order to estimate the heat transfer, we go to the saturated steam table again to estimate the change of enthalpy. M times H sub Fg. So we get the heat transfer term, and when we divide by the temperature, make sure we put the environment temperature, 25 degrees C, as the denominator. Then we get the entropy change for the environment. Combine these two terms, we get a positive quantity. So it doesn't violate the second law of thermodynamics. Entropy generation, when we combine the system and the environment, entropy generation has to be positive. Let's look at the third example. If we have a resistor, a heating element inside a space heater as the control volume, the electrical power provides 1 kilowatts of energy to the resistor. Then the heat from the resistor will dissipate to its environment. If we take the second control volume like this, control volume 2 has contact with the heating element. On the right, it has contact with the environment at the 20 degrees C. The heating element is at 600 K, very high temperature. Let's look at the entropy generation of the control volume of the heating element and the control volume 2. The electrical power we provide to the heating element is essentially the energy transfer out of the control volume. So we can say the power generation equal to the rate of heat transfer. That's from the first law. If we would like to look at the entropy balance equation for control volume number 1, in the steady state, the control volume rate of entropy change is 0. On the right, we have one term associated with heat transfer out of the heating element, that's this term, plus the entropy generation rate. If we solve this portion of the equation, we get entropy generation equal to Q rate of heat transfer out divided by temperature of the wire. We get this quantity. Let's look at the second control volume. If we have taken this control volume like the glass window we just looked at it. At the one side, we have heat transfer into the control volume. At the other side, we have heat transfer out of the control volume. In the steady state, we have left-hand side equal to 0. On the right, we have two heat transfer terms and one entropy generation term. The first heat transfer term is for the left-hand side. So the wire surface will be consider the temperature of the control surface. The second term is associated with heat transfer to the big reservoir. And reservoir temperature will be used in the denominator for the second heat transfer term. Then move the entropy generation, turn to the right, to the left, we get combination of these two terms. In the steady state, these two Q terms have the same absolute value. Ambient temperature will be lower than the wire surface temperature. Therefore, the right-hand side of this equation is always positive. So for both control volume, we have positive entropy generation terms. before we leave the slide, we also need to grab the key concept of these three examples. All the three examples we discussed involve heat transfer. And within the heat transfer process, it involves heat transfer between two objects with finite temperature difference. This finite temperature difference causes irreversibility. The irreversibility causes entropy generation. Entropy generation causes lost work. Now let's look at the slightly more complicated case, which involves a heat pump used to warm the house in the winter. If the heat pump withdraws the heat at 8 degrees C underground to a house, consider the house is a high temperature reservoir at 21 degrees C. In our first part of analysis, we consider three independent control volumes. The first one involves the low temperature reservoir heat transfer to the control volume. Control volume gives the heat to the heat pump. And in the analysis of second control volume, the control volume has contact with heat pump on one side, with contact with the high temperature reservoir on the other side. And for the heat pump, the fluid is running in the cyclic process. And notice we have two other temperatures listed here. These represent the lowest possible temperature needed for a heat pump. This represents the highest temperature the fluid need to reach in order to achieve the goal. Why we need such high and such low temperatures? This is actually related to what we discussed earlier. If we have a heat engine with the temperature reservoir designated by TL and the TH, the heat pump absorbs energy from low temperature reservoir. So the temperature has to be lower than T sub L. This is the reservoir temperatures. And T sub LOW, T low, is at a minus 10 degrees C. So there's a finite difference that causes irreversibility. If we look at the high temperature reservoir, it's set, the reservoir is at the T sub H, but the fluid running in the heat pump must be at a higher temperature to achieve the heat transfer. Heat always transfers from high temperature to low temperature. Therefore, in order to reject the heat to the high temperature reservoir, the fluid temperature in the heat pump must have a temperature higher than T sub H. Then we can draw the third control volume like this. it has work going in. The fluid actually have two temperatures. One is at a -10, the other one is a 50, higher temperature. And if we would like to analyze the entropy change for each one of these control volume, then let's look at the heat pump. Heat pump involve heat transfer, two heat transfer term, and one entropy generation term. And substitute what we are given. We are given this heat transfer quantities. Let's see, 10 kilowatts of power input, that's the Q, and the COP of the heat pump is 4. The 4 temperature are given. It's not state, these two Q terms are not stipulated, but it's in the example in section 5.10. So assume these two heat transfer terms are given, we can get a entropy generation term for the heat pump. Then we can analyze the two other control volumes. Each one will have two heat transfer terms and one entropy generation terms. And notice we can do similar analysis for each control volume, CV1, CV2, like here. Then finally, we combine all this. That means we combine all these 3 control volume like one control volume. We could do that, and the result is the summation of these 3 control volume we analyze it. And the resultant expression actually is just like this heat transfer term, this heat transfer term, independent of the heat pump term. But in all these 4 control volumes, we have positive energy generation, entropy generation terms. Positive, 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 combined positive terms. Here we would like to make 2 more comments. The resultant combined analysis yield a simplified analysis. Essentially, we take a control volume like this. We can generate this result too. But we'd like to caution you one thing. More detailed analysis like we went through give us more information about the cause of irreversibility. That is why we go through a more complicated analysis like we did. And of course, in this analysis, we discuss the source of irreversibility clearly. Now, when we apply the entropy generation concept and the lost work concept into the heat engines and the heat pump, we get some interesting results. First, look at the first law. In the steady state, a heat engine, we have this equation. And entropy balance equation, we have this equation. We have an entropy generation rate. And solve the second equation for QL dot, we get this equation. Solve this equation for QL dot. And substituting this expression in the first law equation, we get this. And rearrange, we get this equation. If we look at the similar equation we generate for reversible process in the last chapter, we do not have the last term. For a Carnot cycle, we have this term only. So this term is essentially the lost work, rate of the lost work. And another aspect of the entropy generation term can be stated as the following. If we said for idealized Carnot cycle, we have the definition of efficiency like W divided by QH, we don't have the last term. But if we put the lost work here in this final expression, we have a force QH dot. In this equation, we can combine these two terms. Force QH dot 10 in there. We said this is the efficiency of an actual pump. So we can say this expression is useful if we are given a situation we know the actual efficiency of a pump. We know how much heat it absorbs. We know how much shift work it does. We can get efficiency. It can be expressed in this way. This is the actual shift work, actual work being absorbed. These two expressions will be useful for solving a wide range of problems. Similarly, for heat pumps, we can analyze in the similar way. Energy balance generate this expression, entropy balance equation, in the steady state. Both equations have left zero on the left side. And solve for QH from this equation, and then substituting QH in the energy balance equation, we have this equation, and rearrange, solve this for QL, we have this equation. If we compare this equation to its counterpart for the reversible process we discussed in chapter 5, we do not have the second term at all. So that means for reversible process, we have this term only. For a irreversible process, the entropy generation cause the QL to be lower. The energy efficiency become lower because they extract lower energy, lower amount of energy from the low temperature reservoir. Then if we use the definition of COP for the idealized case, Carnot cycle, this portion is the definition of COP for idealized situation. For a irreversible heat pump with irreversibility that cause work loss. So we have a loss term. So we can express the actual heat, actual COP, like the COP times the actual work done by the pump. These are two useful expressions for solving a group of homework problems. So I will conclude this chapter by making a few statements. Number one, the entropy generation term is caused by irreversibility. The higher the irreversibility causes higher the entropy generation. Therefore, for heat engine, the highest possible work can be performed by a heat engine is due to very low entropy generation. Similarly, for a refrigerator, the maximum energy can be extracted by a heat pump is due to lowest entropy generation at a given power given to the pump. And for the Carnot cycle process, the engine and the pump have highest efficiency, and they correspond to zero entropy generation. For the higher the irreversible process, it causes higher entropy generation. Here, I emphasize irreversibility causes entropy generation. Entropy generation causes loss work. And here for this course, temperature difference during the heat transfer usually is the major source of irreversibility. Now, this is the conclusion of chapter 6.